Our goal this week is to continue our study of tangent measures, and in particular to present some of the ideas and methods of Price's theorem, the result of which the theory of tangent measures derives. The first new tool that we need is a metric on the space of radon measures. So given two radon measures mu and nu, and a ball B, we define the distance between mu and nu in the ball B, denoted f sub b of mu and nu, to be the supremum over all one Lipschitz functions supported in the ball B of this difference between the integrals of f with respect to mu and nu respectively. For any positive radius r, we'll use the shorthand notation f sub r to denote f sub b0r. So in other words, f sub r is going to denote the distance between two measures in the ball center at 0 radius r. And when given a single measure mu, we're going to write f sub r of mu to denote the distance from mu to the 0 measure inside the ball of radius r. Now, in this case, one can actually figure out what the one Lipschitz function supported in this ball is that achieves the supremum in the definition of fr of mu 0. And it's going to equal the positive part of the radius of the ball minus the norm of z. So you can think of this quantity fr mu as a sort of norm on the space of radon measures, but you have to be careful with this interpretation since for us radon measures are non-negative set functions, and so in particular they don't form a vector space. We record here a few key properties that are not too difficult to verify on your own. So given a radon measure mu in Rn, we first have that the fr distance is monotone in R. So fr of mu is at most f of s mu when r is strictly less than s. Secondly, the distance between two measures in a ball center at a of radius r is equal to r times the distance in the unit ball between the blown up versions of those two measures, i.e. the measures pushed forward under the blow up map that takes the ball bar to the unit ball. And finally, after applying property 2 to the case that one of the measures is equal to 0, this gives that the f, quote-unquote norm of mu in the ball center at a of radius r is equal to r times the f norm of the push forward of mu to the unit ball. Using the fr distances, we can characterize weak convergence of radon measures. So given a sequence of radon measures mu sub I, the sequence mu sub I converges weakly to a measure mu if and only if the fr distance of mu I to mu converges to 0 for every radius r bigger than 0. So let's first prove the forward implication. So let's suppose we have a sequence of measures mu I converging weakly to another radon measure of mu. Now recall from the definition of fr of mu I and mu, this was this supremum of differences of integrals over mu I and mu of one Lipschitz function supported in the ball center at 0 radius r. So what we're going to do is for each I, pick a Lipschitz function that almost achieves that supremum. So I'm going to so for all I, there exists f sub I, that's one Lipschitz, and supported in the ball center at 0 radius r, such that if we look at the integral of fi d mu I minus the integral of fi d mu, this is greater than fr of mu I mu minus 1 over I. Okay, now notice that because the fi are one Lipschitz and supported inside the ball center at 0 radius r, so that means that they vanish outside the unit ball, and this implies that they're uniformly bounded. And in fact, the maximum value that they could achieve inside the ball centered at 0 radius r is at most the radius of r. So we have a uniformly bounded sequence of one Lipschitz functions. Therefore, our Zerla-Ascoli implies that we can pass to a subsequence okay, and I'll use the same subscripts as before, such that f of I converges uniformly to some other one Lipschitz function f supported in the ball center at 0 radius r. Okay, so thus, let's look at fr of mu I mu. So this was less than 1 over I, by this inequality over here, 1 over I plus this difference of integrals. Now what I'm going to do is I'm going to add and subtract f from the first of these integrals and then apply the triangle inequality. So that absolute value up there is at most the integral of f sub I minus f d mu, d mu I, plus the integral of, plus the absolute value of the integral of f d mu I minus the integral of f d mu. Okay, now we observe that because fi is converging uniformly to f, and these functions are both supported in the unit ball, that will mean that this whole integral is actually just going to 0. Since this integral we can bound above by the L infinity norm of the difference between fi and f times the measure of the ball, which is finite since mu is radon. So this will go to 0. Now, if we look at the second integral, notice now that these two integrals have the same function f in them. And f is a continuous function of compact support. And because mu I is converging weakly to mu, that by definition means that the integral of f d mu I is converging to the integral of f d mu. So that implies that this absolute value also converges to 0. And finally, of course, 1 over I goes to 0. So this whole thing is going to 0. So this implies fr of mu I mu is converging to 0, and for every radius r bigger than 0. Now let's show the other direction. So let's suppose that fr of mu I mu is going to 0 for all radii are bigger than 0. So we'll show that this implies mu I is converging weakly to mu. But this is actually a lot simpler. So let phi be a C infinity function with compact support in Rn. So you can show that this space of functions is dense in the space of continuous functions vanishing at infinity. Okay, so thus, if we want to show that mu I is converging weakly to mu, it turns out that it suffices just to show that the integral of phi with respect to mu I converges to the integral of phi with respect to mu for phi in this dense subclass. So, in other words, what we want to show is that the integral of phi d mu I converges to the integral of phi d mu for every such C infinity function phi. Or in other words, we want to show that the absolute value of this difference converges to 0 for every C infinity function phi with compact support. So what we do, so let's let r be bigger than 0 such that the support of phi is contained in B0r. Then, if we do this, this is almost immediate. So notice that phi, because it's C infinity, that means that it is a Lipschitz function. Although the Lipschitz constant is not necessarily 1, it will be the L infinity norm of the derivative. But what that implies then is that because the function phi is supported in this ball center at 0 of radius r, that means that this is at most the Lipschitz constant of phi, which is the infinity norm of the derivative, times the fr metric between mu I and mu. Okay, but by assumption, this is going to 0 as I goes to infinity. And this implies that this difference goes to 0. And since that holds for every C infinity function phi with compact support, that implies weak convergence. Now, technically, these f functions that we've defined are pseudometrics, not metrics, since if we look at f b of mu nu, okay, if this is equal to 0, all that says is that the measures mu and nu are equal to each other in the interior of the ball B. However, we can combine these pseudometrics into one metric as follows. So we can define the metric d of mu comma nu to equal the sum, this linear combination of the minimum of 1 and the f metrics in the ball's center at 0 of radius 2 to the j. Okay. Then not only will this give us a metric on the space of radon measures, but the space of radon measures will be a complete metric space under this metric. However, we'll more often work with these individual pseudometrics f sub r instead of the above metric. We end this lecture by mentioning that the space of radon measures is separable with respect to these pseudometrics, or, if you will, with the metric defined on the previous slide, in the sense that we can find there exists a countable dense subset of the space of radon measures. That is a countable dense set so that for any radon measure mu and any radius r that we specify, we can find an element of our dense class as close to mu as we wish in the ball center at 0 of radius r. We won't show the details, but we'll describe the dense class explicitly. So in particular, recall that delta k denotes the set of dyadic cubes of side length 2 to the minus k. So notice as the integer k increases, the size of the cubes in this set decrease. Then our dense class is the union over all integers k of all rational linear combinations of Dirac masses positioned at the centers of these cubes, where xq denotes the center of a cube q in the set of dyadic cubes delta sub k. Then it can be shown that for a given radon measure mu, if we look at the sum of Dirac masses centered at the centers of dyadic cubes in delta k, and with coefficients fk of mu q, so this is going to be we define this to be the closest multiple of 2 to the minus j to the number mu of q. So if we take this explicit rational linear combination of Dirac masses as our measure mu k, then you can show that mu sub k converges weakly to the measure mu. And in particular, by the results from earlier, f sub r of mu with mu k will converge to 0 for all radii r bigger than 0.